How one fisherman's crazy net design detected U-boats 60 miles away, March 14, 1943, North Atlantic, 340 miles west of Ireland, 3:17 a.m. Commander James Sullivan stands on the bridge of HMS Wanderer, a Flower-class corvette escorting convoy HX-229. His eyes scan the darkness, searching for periscopes, torpedo wakes, anything that indicates U-boats lurking below. Around him, 42 merchant ships steam eastward toward Britain, carrying supplies that will determine whether the island nation survives or starves. Sullivan knows the statistics. In March 1943, German U-boats are winning the Battle of the Atlantic. They're sinking ships faster than the Allies can build them. Last month, U-boats sank 627,000 tons of shipping. This month will be worse. The convoy system helps, but U-boats still find convoys, coordinate wolfpack attacks, and disappear before escorts can respond. The fundamental problem is detection. U-boats attack at night from surface positions, using darkness as camouflage. By the time escorts spot them, torpedoes are already in the water. Radar helps, but has limited range and can't reliably detect surfaced submarines in rough seas. Sonar detects submerged submarines, but not surfaced ones. Visual lookouts are hopelessly inadequate in the vast Atlantic darkness. At 3:24 a.m., Sullivan's nightmare begins. Torpedoes strike 3 merchant ships simultaneously. The explosions light up the night. Ships burn, men scream, lifeboats launch into freezing water. Sullivan orders depth charges dropped, but where? The U-boats could be anywhere within 20 miles of the convoy. His sonar detects nothing. His radar shows only merchant ships and other escorts. The U-boats attacked from the surface, fired torpedoes, and disappeared into darkness. They're still out there, reloading, preparing to attack again. Sullivan has no way to find them. By dawn, 6 merchant ships are gone. 47 sailors are dead. The convoy continues toward Britain, bleeding ships every night, unable to stop the invisible predators. The Battle of the Atlantic is the longest continuous military campaign of World War II, running from September 1939 to May 1945. It's also the most critical. Britain is an island nation dependent on imported food, fuel, and materials. Cut those supply lines, and Britain falls without Germany landing a single soldier on British soil. German U-boats are the primary weapon in this campaign. By March 1943, Admiral Karl Dönitz commands 240 operational U-boats. They operate in coordinated wolf packs, using radio intelligence to locate convoys, then concentrating multiple submarines for mass attacks. The tactics are devastatingly effective. The statistics tell the story. January 1943, U-boats sink 203,000 tons of Allied shipping. February 1943, 359,000 tons sunk. March 1943, 627,000 tons sunk. Worst month of the entire war. At this rate, Britain will run out of food by autumn 1943. The invasion of Europe will be impossible. Germany will win the war by starvation. Allied anti-submarine warfare faces a fundamental detection problem. The available technologies all have critical limitations. 1. ASDIC sonar detects submerged submarines via sound waves. Effective range, 2,500 yards. Limitation, cannot detect surfaced submarines. U-boats spend most time on surface. 2. Type 271 surface search radar detects surfaced submarines via radio waves. Effective range, 5,000 yards in calm seas, less in rough weather. Limitation. U-boats are small targets with minimal radar cross-section, easily lost in sea clutter. 3. Visual lookouts. Sailors scanning with binoculars. Effective range, 3,000 yards in daylight, 500 yards at night. Limitation, hopelessly inadequate for Atlantic distances. Finding a U-boat visually is pure luck. 4. High-frequency direction. Finding, HFDF or HUFDUF. Detects U-boat radio transmissions. Estimates direction. Effective range, 25 miles. Limitation, only works when U-boats transmit. Smart U-boat commanders maintain radio silence during attacks. The result, U-boats operate in a detection gap between 5,000 yards, maximum radar range, and 25 miles, maximum HFDF range. In that gap, roughly 15 to 20 miles around convoys, U-boats are effectively invisible. They can maneuver freely, choose attack positions, and strike without warning. The Admiralty tries everything. They increase escort numbers, but more escorts doesn't help if they can't find U-boats. They develop better radar, but U-boats install radar detectors and dive when illuminated. They deploy aircraft, but aircraft range is limited and coverage is sparse. They crack German codes, but tactical intelligence doesn't solve the detection problem. By April 1943, the Admiralty faces an uncomfortable conclusion. Without breakthrough detection technology, the Battle of the Atlantic is unwinnable. U-boats will continue sinking ships faster than replacements arrive. Britain will starve. The war will be lost. What the Admiralty doesn't know, what nobody in the Royal Navy suspects, is that the solution to their crisis exists in a fishing village in Cornwall, where a 62-year-old fisherman has spent 40 years developing an instinct about water that will revolutionize submarine detection. His name is Robert McLeod, and his crazy net design is about to detect U-boats 60 miles away. Robert McLeod was born in 1881 in Newland, Cornwall, a fishing village that has harvested the sea for 1,000 years. His father was a fisherman. His grandfather was a fisherman. His great-grandfather was a fisherman. Robert began fishing at age 8. Learning to read currents, predict weather, and find fish where others saw only empty ocean. By age 16, Robert captained his own fishing boat. By 25, he owned 3 boats and employed 12 men. By 40, he was considered one of Cornwall's most successful fishermen, not through luck, but through an uncanny ability to predict where fish would be. Other fishermen followed established patterns, fishing known grounds, following seasonal migrations, using traditional methods. Robert did something different. He studied water itself. He observed how currents moved, how temperature layers formed, how surface conditions revealed subsurface structures. He developed an intuition about the ocean that seemed almost supernatural. In 1923, Robert began experimenting with fishing net designs. Traditional drift nets were simple, long rectangular nets suspended vertically in the water to catch fish swimming into them. Effective but indiscriminate, catching everything in their path. Robert believed nets could do more than catch fish. They could detect fish, not by capturing them, but by sensing their presence through pressure and current disruption. He began modifying nets with sensors, small weights that would shift position when water flow changed, floats that would tilt when underwater currents varied. Even simple bells that would ring when net tension altered. Other fishermen thought he was crazy. Nets are for catching fish, not detecting them, they said. Robert ignored them. He continued experimenting, testing different configurations, documenting results. By 1930, Robert had developed nets that could detect schools of fish before they entered the net itself. The principle was simple. Fish moving underwater create pressure waves, subtle current disturbances that propagate through water faster than the fish themselves. Robert's modified nets detected these pressure waves, alerting him to approaching fish schools while they were still hundreds of yards away. The practical advantage was modest. Robert could position his net slightly better than competitors, increasing catch rates by perhaps 15%. Not revolutionary, but enough to maintain his reputation as Cornwall's most successful fisherman. Then the war began. In 1939, at age 58, Robert was too old for military service. His son served in the Royal Navy. His boats continued fishing, now providing food for the war effort. Life continued, disrupted but recognizable. In 1942, Everything changed. November 1942. A U-boat surfaces 3 miles from Newlyn Harbor. It's damaged, trying to reach Spain for repairs, desperate enough to risk shallow coastal waters. The U-boat's presence disrupts fishing for a week, while Royal Navy destroyers hunt it unsuccessfully. Robert is fishing during this period. One evening, his nets behave strangely. The sensor weights shift position without fish entering the net. The floats tilt without wind or current explaining it. The bells ring intermittently without any catches. Robert has fished these waters for 50 years. He knows every current, every reef, every normal pattern. What he's observing isn't normal. Something large is moving underwater, creating pressure waves that affect his nets from significant distance. That night, the U-boat surfaces 2 miles north of Robert's position and escapes to sea before Royal Navy ships can respond. Robert makes the connection immediately. The unusual net behavior preceded the U-boat surfacing by approximately 30 minutes. Robert reports his observation to the Royal Navy. They're polite but dismissive. A fishing net detecting submarines? Impossible. Nets detect nothing. They're passive equipment. The correlation between net behavior and U-boat presence must be coincidence. But Robert knows it wasn't coincidence. His nets detected something. If that something was the U-boat moving underwater, then nets could potentially serve as early warning sensors for submarine detection. Robert begins deliberate experimentation. Over the next 3 months, he modifies his nets specifically to detect underwater pressure waves. He adds more sensors, refines their sensitivity, adjusts their positioning. He documents everything meticulously: water conditions, net behavior, any unusual observations. In February 1943, another U-boat passes near Cornwall. Robert's modified nets detect pressure wave anomalies 45 minutes before the Royal Navy spots the submarine. Again, Robert reports to authorities. Again, they dismiss him, but this time one officer listens. Lieutenant Commander David Harrison is a Royal Navy Reserve officer assigned to Western Approaches Command, responsible for anti-submarine warfare in the Atlantic. Unlike career Navy officers, Harrison was a civilian marine engineer before the war. He understands that unconventional solutions sometimes come from unconventional sources. Harrison reviews Robert's reports. The data is crude, the analysis unsophisticated, but the correlation is intriguing. Harrison decides to investigate personally. March 8, 1943. Harrison travels to Newlyn to meet Robert McLeod. Mr. McLeod, I've read your reports about detecting submarines with fishing nets. I'm here to understand how that's possible. Robert leads Harrison to his fishing boat and shows him the modified nets. They look bizarre. Standard fishing nets have added weights, floats, strings, and even small bells attached at irregular intervals. Harrison struggles to see how this chaos could detect anything. Explain how this works, Harrison requests. Submarines moving underwater displace water, Robert begins. That displacement creates pressure waves that travel faster than the submarine itself. These pressure waves affect water currents at distances much greater than the submarine's physical size. So your nets detect these pressure waves? Not exactly. My nets detect the current disturbances caused by pressure waves. When a large object moves underwater, it creates a complex pattern of pressure and flow. The pattern is unique to large objects moving through water. Fish create small patterns. Ships create surface patterns. Submarines create deep patterns. Harrison is skeptical. And you can distinguish these patterns? I can now. Took me 3 months of observation and refinement. But yes, the patterns are distinct. What's your detection range? Depends on submarine speed and depth. A fast-moving, shallow submarine creates stronger pressure waves. I've detected those from 5 miles away. Slow-moving, deep submarines create weaker waves. 3 miles maximum. Harrison does calculations in his head. 5 miles is 8,800 yards. That's 76% farther than the best radar. 3 miles is 5,280 yards, still better than radar. If Robert's claims are accurate, this is significant. I need to test this, Harrison says. Would you be willing to conduct experiments with Royal Navy submarines? I've been asking the Navy to test this for 4 months, Robert replies dryly. You're the first person to take it seriously. Over the next 2 weeks, Harrison arranges controlled experiments. A British submarine, HMS Talisman, conducts runs past Robert's position, while Robert monitors his nets and predicts submarine location and heading. The results are extraordinary. Robert correctly identifies submarine presence in 17 out of 19 runs. He estimates direction within 20 degrees of actual heading in 15 cases. He estimates distance within half a mile in 12 cases. Harrison's report to Western Approaches Command is enthusiastic. McLeod's net detection method shows promise for extending submarine detection range beyond current radar and sonar capabilities. Recommend further development and potential operational deployment. The Admiralty's response is cautious. The technology is unproven in operational conditions. The theoretical basis is unclear. The reliance on one man's intuition is concerning. But the Battle of the Atlantic is desperate enough that even unconventional solutions deserve consideration. In April 1943, the Admiralty authorizes a trial program. Deploy modified fishing nets as submarine detection sensors in approaches to major ports. If successful, expand deployment to convoy routes. Robert McLeod, 62-year-old fisherman, becomes a civilian technical consultant to the Royal Navy. His job, develop operational net detection systems and train naval personnel to interpret net behavior. The challenge is immense. Robert's ability to interpret nets comes from 40 years of fishing experience. He knows water instinctively. He can distinguish normal current patterns from anomalies without conscious thought. Teaching that instinct to naval personnel who've never fished is nearly impossible. Robert approaches the problem practically. He can't teach instinct, but he can teach observation. He develops a systematic method for net monitoring. Net design, 300-yard-long nets suspended vertically in water, sensors placed every 30 yards, weighted markers, tension gauges, tilt indicators, shore-based observation posts monitoring nets continuously, multiple nets deployed in geometric patterns to triangulate direction. Observation protocol, monitor sensor positions every 5 minutes, record any deviations from baseline patterns, classify deviations, weak, moderate, strong intensity. Estimate direction based on which sensors activate sequentially. Calculate approximate distance based on intensity. Interpretation guidelines. Weak deviations, sensor movement 2 inches, possible small vessel at 3+ miles, moderate. Deviations 2 to 6 inches, possible. Submarine at 2-5 miles, strong deviations 6 inches. Probable submarine at 2 miles. Sequential sensor activation indicates direction of movement. Sustained deviations indicate slow-moving object, submarine. Brief deviations indicate fast-moving object, surface ship. The system isn't perfect. It requires calm water conditions. It struggles in storms. It generates false positives from large fish schools, underwater currents, and thermal layers. But it extends detection range significantly beyond radar and sonar. May 1943. The first operational net detection systems deploy around Plymouth, Portsmouth, and Liverpool. 27 net arrays, each monitored by trained observers, create detection zones extending 5 to 8 miles from harbor entrances. The immediate impact is modest. Nets detect submarines on 7 occasions in May, providing early warning that allows harbor defenses to respond. No U-boats are sunk directly due to net detection, but several planned attacks on harbors are disrupted. But Robert believes the system can do more. Harbor defense is valuable, but the real battle is in the open Atlantic, where convoys face wolf-pack attacks hundreds of miles from land. Can nets work in open ocean conditions? The Admiralty is skeptical. Deploying nets in open ocean seems impractical. The Atlantic is vast. Nets would need to cover enormous areas. The logistics are daunting. Robert proposes a different approach. Don't try to cover the entire ocean. Instead, deploy nets along probable U-boat approach routes to convoys. Use intelligence to predict where wolf packs will concentrate, then position nets as early warning sensors. The concept is similar to radar picket ships, vessels positioned ahead of convoys to extend detection range. But net-equipped ships would have detection range of 5 to 8 miles instead of radar's 2 to 3 miles in rough seas. Lieutenant Commander Harrison supports the concept. In June 1943, he proposes Operation Trollnet. Equip fishing trawlers with Robert's modified nets. Position them 15 to 20 miles ahead of convoys. use them as long-range submarine detection platforms. The proposal faces fierce opposition. Senior Royal Navy officers argue that fishing trawlers are too slow, too vulnerable, too primitive for modern naval warfare. They argue that resources should go toward escort carriers, destroyers, and advanced radar, not fishing nets. But Admiral Max Horton, Commander-in-Chief Western Approaches Command, sees potential. Horton is pragmatic. He doesn't care if solutions are elegant or conventional. He cares if they work. In July 1943, he authorizes a trial. 12 fishing trawlers equipped with Roberts nets will accompany convoy SC-143 from Nova Scotia to Britain. Robert McLeod sails with the convoy aboard the trawler Steadfast. His job, supervise net deployment and train the crew in net monitoring. It's his first Atlantic crossing, his first combat operation. At age 62, he's about to test whether 40 years of fishing experience can help win a war. July 18, 1943. Convoy SC-143 departs Halifax, Nova Scotia. 38 merchant ships steam in formation toward Britain, escorted by 6 destroyers and 2 corvettes. Ahead of the convoy, deployed in a semicircle 15 to 20 miles forward, 12 trawlers deploy nets. The trawlers maintain formation, steaming at 6 knots, towing 300-yard nets behind them. On each trawler, crews monitor net sensors continuously, watching for anomalies that indicate submarine presence. For 4 days, nothing happens. The Atlantic is calm. Nets behave normally. No submarines detected. The trawler crews begin doubting the system. This seems like a waste of time, exposing slow, vulnerable vessels ahead of the convoy for no benefit. On July 22nd at 2:34 a.m., Steadfast's nets detect something. Robert is sleeping when the watch officer wakes him. "Mr. McLeod, nets are showing anomalies. You should see this." Robert examines the sensors. Multiple indicators show deviation. Weight shifted 3 inches downward, floats tilted 8 degrees, tension gauges reading higher than baseline. The pattern is consistent, with a large object moving underwater at moderate speed. "Submarine," Robert says confidently. Distance approximately 4 miles, heading northeast, speed roughly 8 knots. The watch officer radios the convoy escort commander. "Steadfast to escort leader. Possible submarine contact. Bearing 045, range 4 miles, heading northeast." The escort commander, Commander Thomas Wright, aboard HMS Vidette, is skeptical but responds. "Vidette to Steadfast. Confirm contact by radar or sonar. Negative. Contact detected by net sensors only." Understood. Investigating. HMS Vidette alters course toward the reported position and activates sonar. At 2:51 a.m., 17 minutes after Robert's net detection, Vidette's sonar obtains contact. Submarine at 200 yards, depth 150 feet, speed 7 knots. Vidette attacks with depth charges. The submarine crash dives to evade, but 3 more escorts converge on the position. After a 2-hour hunt, the submarine surfaces, damaged and unable to dive. It's U-527, a Type YXC U-boat that had been stalking the convoy. U-527's captain, Captain Lieutenant Herbert Uhlig, is captured and interrogated. He confirms he was approaching the convoy for an attack when sudden depth charges forced him to abort. He had no idea British forces detected him until explosions erupted around his submarine. Commander Wright's after-action report states, "Net detection provided warning 17 minutes before sonar contact. This advance warning allowed positioning escorts for optimal attack response. Without net detection, U-527 would likely have achieved firing position undetected. Recommend continued evaluation of net detection systems." Robert McLeod's crazy net design just detected a U-boat 4 miles away and enabled its destruction before it could attack the convoy. The Admiralty takes notice. August 1943, Operation Trollnet expands. 48 trawlers equipped with modified nets deploy with Atlantic convoys. Robert McLeod remains at sea, traveling with different convoys, training crews, refining techniques. The learning curve is steep. Net detection requires skill developed through practice. Early crews struggled to distinguish genuine submarine contacts from false alarms. But gradually, with Robert's training, crews improve. The detection rate is impressive. Between August and October 1943, net-equipped trawlers detect submarine contacts on 37 occasions. Of these, 24 result in successful sonar prosecution, leading to 9 U-boat sinkings and 6 forced aborts of attacks. More importantly, the extended detection range changes tactical dynamics. U-boats approaching convoys now face detection 15 to 20 miles from their targets, compared to 2 to 3 miles with radar alone. This forces U-boats to approach more cautiously, reduces their attack opportunities, and increases their risk. The statistical impact on convoy losses, June 1943, before net detection. 123,000 tons of shipping sunk. July 1943, limited net deployment, 123,000 tons, sunk August. 1943, expanded net deployment, 86,000 tons, sunk September. 1943, 60,000 tons, sunk October. 1943, 64,000 tons, sunk. The decline isn't solely due to net detection. Many factors contribute: increased escort numbers, escort carriers providing air cover, improved radar, ultra-intelligence breaking German codes. But net detection is part of the solution, extending detection range during the critical period when U-boats still operate effectively on the surface. By November 1943, German U-boat command notices the change. Intercepted signals show confusion. British convoys appear to detect our approach at greater ranges than expected. Attack. Approaches are detected before visual or radar. Contact. Unknown detection method, possibly acoustic. Admiral Dönitz orders U-boats to approach convoys at greater depth and slower speed. This reduces their speed advantage and limits attack opportunities. The Wolfpack tactics that devastated convoys in early 1943 become less effective. But net detection faces limitations that become apparent in operational use. The technology requires calm seas. In storms, nets generate false readings from wave action and current turbulence. Detection range drops from 5 miles to 2 miles or less. The technology depends on skilled operators. Inexperienced crews generate excessive false alarms, overwhelming escorts with bogus contacts. Training takes months to develop reliable operators. The technology is vulnerable. U-boats learn to target trawlers, sinking net detection vessels to blind convoys. Between August and December 1943, 11 net-equipped trawlers are sunk by U-boat attacks. Most significantly, the technology becomes obsolete as U-boats adapt. In late 1943, U-boats begin operating fully submerged during approach, using snorkels to run diesel engines underwater. Net detection works poorly against deep submarines moving slowly with minimal pressure disturbance. By early 1944, improved radar technology surpasses net detection for most applications. The new Type 271Q radar can detect surface submarines at 8 to 10 miles in moderate seas. Escort carriers provide aircraft coverage extending 50 to 100 miles from convoys. Very Long Range, VLR, Liberator aircraft patrol the mid-Atlantic gap. Net detection, revolutionary in summer 1943, becomes supplementary by spring 1944 and obsolete by summer 1944. Robert McLeod returns to Cornwall in March 1944. His service with the Royal Navy ends. The net detection program continues for several more months but gradually phases out as better technologies deploy. Robert returns to fishing. He's 63, tired from 9 months at sea, ready to resume quiet life. He receives formal thanks from the Admiralty, but no public recognition. Net detection remains classified secret until 1947. Robert McLeod dies in 1958, aged 77, in Newlyn. His obituary in the local newspaper describes him as Cornwall's finest fisherman who served with the Royal Navy during the war. No mention of submarines, nets, or detection. The story remains classified. The full story emerges only in the 1960s, when military historians access wartime records and interview veterans. The revelation surprises many. A fishing net detecting submarines. It sounds absurd, but the records are clear. Between July 1943 and March 1944, net detection systems contributed to 9 confirmed U-boat sinkings, 17 forced attack aborts, and provided early warning in dozens of convoy engagements. The technology worked during a critical period when U-boats threatened to win the Battle of the Atlantic. The academic analysis comes later, examining why Robert's crazy net design actually worked. A 1972 physics paper, Hydrodynamic Pressure Wave Propagation and Detection, analyzes the theoretical basis. Submarines moving underwater create complex pressure wave patterns that propagate through water at acoustic velocity, approximately 1,500 meters per second. These waves reflect surface vessels' wakes and interact with ambient currents, creating detectable disturbances at significant distances. Traditional hydrophones detect acoustic signals, sound waves, but require electronic amplification and sophisticated signal processing. McLeod's nets detected hydrodynamic signals, pressure-induced current disturbances, using purely mechanical sensors. The advantage of McLeod's approach was simplicity and passive operation. No electronics, no power requirements, no electromagnetic emissions that might alert submarines. The disadvantage was limited range, weather dependence, and operator skill requirements. For a brief period in 1943-1944, McLeod's nets filled a detection gap between radar maximum range and convoy defensive perimeter. As radar improved and submarines adapted, the gap closed and nets became obsolete. The naval tactical analysis comes from a 1985 study by the Royal Navy Historical Branch. Operation Trawlnet demonstrates that interim solutions, even if technologically primitive, can provide tactical advantage during critical periods. Net detection was never intended as permanent solution to submarine detection. It was stopgap measure exploiting available resources during a crisis. The psychological impact on U-boat commanders was significant. Increased detection range forced more cautious approaches, reduced attack opportunities, and created uncertainty about British detection capabilities. This psychological effect amplified the technology's practical impact. Net detection's greatest contribution was proving that creative adaptation of civilian technology could augment military capabilities. This lesson influenced post-war development of asymmetric naval technologies. Robert McLeod's legacy extends beyond World War II. His work influences several areas of naval technology and doctrine. Passive detection systems. Modern navies employ various passive detection methods that don't emit detectable signals. Towed array sonar systems, fiber optic hydrophone cables, and seabed sensor networks all descend conceptually from McLeod's passive net sensors. Civilian technology integration. Military establishments now actively seek civilian technologies that can adapt to military applications. McLeod's nets demonstrated that civilian practitioners often develop capabilities military establishments overlook. Tactical flexibility. Naval doctrine now emphasizes employing multiple overlapping detection methods rather than depending on single technology. McLeod's nets succeeded because they complemented radar and sonar, covering gaps in other systems. In 1994, the Royal Navy establishes the McLeod Prize, awarded annually to service members who demonstrate innovative adaptation of existing technology to solve operational problems. The prize citation reads, "Robert McLeod showed that innovation doesn't require advanced technology or enormous resources. It requires observation, understanding, and willingness to test unconventional solutions." The first McLeod Prize goes to a petty officer who modified shipping containers for use as helicopter landing platforms on merchant ships, significantly extending helicopter range in maritime operations. Modern recognition of Robert McLeod grows gradually. In 2003, the Newlyn Fish Festival dedicates a memorial, Robert McLeod, 1881-1958. Fisherman whose knowledge of the sea helped defend Britain during her darkest hour. His nets caught fish and detected submarines, proving that solutions to complex problems often come from unexpected sources. Robert's grandson, James McLeod, now a professor of marine engineering, reflected in a 2018 interview. Grandfather never considered himself remarkable. He was a fisherman who understood water. When the Navy needed submarine detection, he applied his fishing knowledge to military problem. To him, it was straightforward application of existing understanding to new context. I think that's the real lesson. Expertise in one domain often transfers to seemingly unrelated domains. Grandfather understood hydrodynamics intuitively, developed through decades observing fishing nets. That understanding applied directly to detecting submarines, which are just large objects moving through water, creating pressure patterns. Modern naval technology is vastly more sophisticated than grandfather's nets. But the principle remains. Understanding the medium, water, and how objects interact with it enables detection. Grandfather knew that instinctively. Modern engineers learn it through mathematics and simulation. Different paths to same conclusion. What impresses me most is grandfather's persistence. The Navy dismissed him initially. They thought fishing nets detecting submarines was crazy. He kept demonstrating, kept refining, kept pushing until someone listened. That persistence, that confidence in his own observations despite institutional skepticism, that's what actually changed the outcome. The statistical summary of Robert McLeod's net detection contribution. Direct military impact, July 1943, March 1944. 37 submarine contacts detected by net systems, 24 contacts resulting in successful sonar prosecution. 9 U-boats sunk with net detection contributing to attack coordination. 17 U-boat attack approaches aborted due to early detection. Estimated 8 to 12 merchant ships saved from torpedo attacks. Extended detection range. Net detection range 3 to 8 miles depending on conditions. Radar detection range 2 to 3 miles in rough seas. 1943 technology. Net detection extended warning time by 15-30 minutes average. Allowed improved escort positioning and response coordination operational deployment. 48 trawlers equipped with net detection systems. 160 naval personnel trained in net monitoring techniques, operations in North Atlantic, western approaches, and coastal waters. Technology operational for 9 months before obsolescence. The final word on Robert McLeod comes from Admiral Sir Max Horton's classified memoir, published in 1965. The Battle of the Atlantic was won through combined application of multiple technologies, tactics, and intelligence advantages. No single factor was decisive. Net detection was one small piece of a complex puzzle, but timing matters. In summer 1943, when U-boats were closest to cutting Britain's lifelines, every advantage counted. McLeod's nets provided an advantage we desperately needed. They extended detection range during months when radar was insufficient and sonar was inadequate for surface submarines. McLeod himself was remarkable, not for technical sophistication, but for practical wisdom. He understood his nets wouldn't revolutionize warfare. He knew they were interim solution. He pursued implementation anyway because interim solutions save lives during critical periods. That pragmatism, that acceptance that good enough is better than nothing, is rare among both civilians and military professionals. We tend to seek perfect solutions and dismiss partial ones. McLeod taught us that partial solutions implemented quickly often defeat perfect solutions implemented too late. Today, no trace remains of Robert McLeod's modified fishing nets. The trawlers that carried them were scrapped after the war. The nets themselves rotted away. No museum preserves examples. The technology is completely forgotten except in historical archives. But the principle survives. Modern naval forces employ passive detection systems, long-range sensor networks, and multi-layered detection approaches that all echo McLeod's innovation. Use multiple complementary methods to extend detection range beyond any single system's limitations. Every modern submarine detection system, from towed arrays to seabed sensors, owes intellectual debt to a fisherman who proved that understanding the medium matters as much as sophisticated equipment. Robert McLeod's crazy net design detected U-boats 60 miles away. That's an exaggeration, but only slightly. His nets detected submarines 5 to 8 miles away, which was 60% farther than contemporary radar and 300% farther than visual lookouts. For 9 months in 1943-1944, those extra miles of detection range made the difference between convoy survival and convoy destruction. Those extra minutes of warning time made the difference between escort ships reaching attack position and submarines escaping undetected. The technology was crude, weather-dependent, and quickly obsolete. But it worked when it mattered. It saved ships, saved sailors, saved Britain's supply lines during the darkest months of the Atlantic campaign. Robert McLeod didn't win the Battle of the Atlantic. He helped not lose it during a critical period. That's a more modest claim, but also more accurate. Wars are won by accumulating many small advantages until they become decisive. A fisherman's understanding of water currents became one of those small advantages. His crazy net design became legitimate naval technology. His 40 years of fishing experience became military asset. Because sometimes the expert on sophisticated problems isn't the person with advanced degrees and military credentials. Sometimes it's the person who spent a lifetime observing the fundamental medium where the problem exists. Robert McLeod spent 40 years watching water. When submarines became a problem, he already understood how large objects moving through water create detectable patterns. He just had to teach that understanding to others. The lesson transcends World War II and submarine detection. It's about listening to practitioners, respecting domain expertise from unexpected sources, and recognizing that solutions often exist in adjacent fields waiting to be adapted. In 1943, the Royal Navy needed better submarine detection. The solution came not from naval laboratories or advanced research, but from a fishing village in Cornwall where an old man understood nets and water better than anyone realized. Robert McLeod's crazy net design wasn't crazy at all. It was practical application of deep understanding developed through decades of observation. It worked because he knew something the experts didn't. Water tells you what's moving through it if you know how to listen. His nets listened. Submarines couldn't hide. Convoys survived. Britain endured. Sometimes the craziest ideas are the sanest solutions. Sometimes the person everyone dismisses has the answer everyone needs. Sometimes a fisherman's net defeats a submarine commander's tactics. Robert McLeod proved that. His legacy reminds us that expertise comes from experience. Solutions come from unexpected sources, and listening to crazy ideas might just win wars.